Hello everyone. Today we will talk about how to build user-generated games. Building a game requires knowledge and skills in multiple fields. Building highly customized games requires massive data handling and more scalable data processing power. A creation is a collection of data. Our motivation is to provide a full solution to creation. That means the full solution of data organization. A robust infrastructure is also needed to support more complex worlds. That means we should support more data processing power. And if users want to share with friends, the data of the game should be accessed anytime, anywhere. Today, we will discuss how to help users to create their world, how the Yahaha pipeline organizes the data for users, and in infrastructure, how we process the data. When I develop a game, I need to be an all-in-one warrior. I search for art assets, preview the effects, and sometimes, when these assets formats are not standardized, I need to correct the assets by using GDC software. Then, I write code to achieve the desired gameplay, repeatedly adjusting the game experience. The process takes up a lot of time. Sometimes, I need to copy my project to a new developing environment. When I want to share the game with my friends, I need to build a version with the game engine, publish it, and send it to my friends. If I want to release a multiplayer game, I also need to consider how to deploy the server and whether my friends can establish a stable connection. To develop an indie game, I have to consider many things, such as how to manage the project, how to obtain the resources, how to reuse the gameplay scripts, and how to optimize the development process. In traditional development, this process can be very complex, which discourages us from indie game development. A complete solution is provided by Yahaha that can help users to manage all the data in a simple way. Users can start creating with a simple process. When creating a world, we need to first pick assets like models, items, characters, animations, sounds, and scenery from the asset library, or upload our own. Edit them in the hierarchy to compose the scene. Then bind the asset and the logic together to bring the world alive. Sometimes customized scripts are also necessary. In fact, Yahaha will provide more services to support the creation of the user custom worlds. For example, Yahaha Studio for editing, infrastructure for ECS, gameplay, physics, network, and client engine, deployment services, and many other platform services. What the users need to do is to focus on the creative part while Yahaha takes care of the rest. We have encountered many challenges. There are different types of the game. How to provide a high degree of creative flexibility. The complexity of the world created by users is unknown. Sometimes they want more than 100 NPCs. Sometimes they want a big map. How to balance unknown complexities in user-generated content. How to effectively organize the different types of asset data, UGC data, runtime data, and many more challenges ahead. In the following, I will introduce the Yahaha pipeline to address these challenges. The asset library contains a large number of 3D models, materials, VFX, animations, and more. Assets are well categorized, and when users search, they can be easily found. Of course, users can also upload their own assets. Before uploading, we will automatically optimize them by reducing a model vertex count, modifying texture size, controlling effects overdraw, standardizing animation data, or providing optimization suggestions. After these assets are standardized, they need to be uploaded into the cloud build process. Assets will be built into separate parts, such as mesh, texture, shader, or each animation clip. Each part of them is one bundle. During the runtime, the asset will be combined again through the asset serialization data. There are some benefits to break down the resources, such as reducing dependencies, avoiding redundant resources during the loading, updating the minimum amount of resources when assets are updated, and the version management can also be applied for each asset. And updating assets will not affect assets in existing games. In fact, the assets will be split into even more detailed parts. The asset library requires asset meta information. For example, the asset tag will be used for search or used for AIGC. The asset loading policy at runtime requires the profile information. If the memory usage is high enough, it will download the assets with low memory size automatically. The gameplay logic requires serialization data, and the rendering engine only needs render-related assets for presentation. During the runtime, the corresponding level of the assets will be auto-downloaded based on the platform of the current device. And further, the different levels of the asset will be loaded based on the distance to the main camera. After completing the cloud building process, the asset will be uploaded to the nodes distributed globally, reducing the distance between the content and the users, while also ensuring that more users can access the data at the same time, as well as the security and the risk control of the asset data. Next, we talk about how to organize the word. When we finish editing a word, the word data will be saved. A game word consists of many elements, such as asset objects, configuration information, logic scripts, or more. And there may be new information added with each new version. How can we use the universal way to describe the game word? Yahaha has defined the standard transmission formats, which aim to efficiently describe the format of the rich things, as well as more component extensions and compatibility with the component format updates. The core design concept of transmission format is to separate the serialization data, assets, and the game structure, and store the hierarchy and asset ID information of the game through serialization. The description of the word will be stored in binary files. The game structure describes all objects used in the game, including two elements. The scene hierarchy data describes that what should be instantiated in the scene. The results table describes the objects that should be loaded when they are needed. Serialization data describes each object, includes the presentation components, gameplay components, settings, and so on. And this serialization data should contain IDs which reference to the assets, scripts, or smart assets in the asset library. In fact, during the runtime, we use logic data to drive the game, while the presentation assets will be stream-loaded by current runtime environment. Moreover, according to the processing power and hardware type of the current device, and according to the memory budget in the runtime, appropriate assets will be loaded, and appropriate graphic settings will be adjusted. This allows for dynamic adjustment of rendering and memory stress, along with optimized processing the LOD on a logical level. We can process all kinds of complex things. Of course, this may come at a cost of sacrificing some parts. When we have organized the word, we need to start bringing it to life. Gameplay logic is complex, like a spider web. So, we should break down these complex logics, separately into independent gameplay scripts, and then the user can quickly pick the gameplay scripts in a set library and organize them. The main types of the gameplay system that drive the world are divided into several categories. The first type is game flow, which mainly describes the flow of the game, play mode, and gameplay managers. The second type is driven logic, which mainly describes the interaction between all objects in the game, such as skills, abilities, etc. The third type is components, which describes the functional parts of the object, such as marketed as an NPC or character, marked his default abilities. Of course, there are also other parts, such as global game rules, damage formulas, and so on. When creating a set with a gameplay logic, The reference assets on the gameplay component are serialized into the set serialization data. During the runtime, assets can be loaded through the streaming loading based on the set ID in the serialization data. When presentation data is not prepared, it will use the dummy asset instead. In editor time, user can combine the asset and the logic together. We can package them into a smart asset and share it to the other users. In some cases, gameplay logic may not be applicable to specific scenarios. And in these cases, users should script their own logic. We provide detailed API reference introduction and guidance on how to develop games on the Yahaha documentation website, utilizing the Lua programming language to implement different types of the game. Yahaha also offers a way to visual script through the node graph, which is a node-based visual programming tools that provides game developers with a fast and visual way to create the game logic. Node graph and the Lua script will be saved and uploaded to the cloud server. During the runtime, the server and the client will download the scripts that are currently in use, which are dynamically loaded, parsed, and executed during the runtime. Lua and the Node Graph can call Yahaha API for logical scheduling. Yahaha API refers to a collection of platform-independent APIs with network support for Yahaha game development. It aims at providing a structured, performant, and data-oriented game development tools. API can operate on data of the ECS layer through the hybrid component interface. This is the state of the client engine runtime represented in the picture. Blue blocks are the logical components that must be implemented with the few dependencies as possible for running on native server runtime. Red blocks are the presentation components that can be implemented with the game engine APIs. In server runtime, presentation components are only accessed as a component data. No presentation logic will be executed. In addition, during the server runtime, there will also be native server functions available for API layer to call, such as cloud storage, which will access the pure database calls, and the client engine doesn't need to care about it. We also provide many built-in hybrid components to connect the lower ECS layer and the upper API layer. In this way, we can drive the objects with just a few lines of code, which is simple and fast. Here's the sample when calling API from the server side. Through the API calls, the component data of the ECS layer will be changed. But how to synchronize the data between the server and the clients? Imagine writing so many RPC calls in Lua and dealing with the different processing events on the client or server. It will be a disaster. How to effectively handle and synchronize the data? Let me introduce our infrastructure. The words created by the users are unexpected, and the infrastructure must ensure that users have the good experience. So, a performant, powerful data processor is important. Infrastructure needs to know what the data needs to be processed, where the data comes, and finally, where the data goes. First, where is the data? We use a multi-cloud scheduler to deploy and manage the server containers across the clouds at the scale. Server global deployment can offer the best regional coverage. Users can always connect to the closest region and enjoy the low latency gaming experience. For a single deployed server in the client, we have adopted the data-oriented design module as an infra architecture. But why do we use data-oriented design? Let's talk about this first. A word is a data collection. A running word means a collection of data is running. A running word is composed of many driving forces. Different driving forces need a different data resolver. So, if data is different, the words need a different driving force to resolve the data. Following the DoD principle, all the commands that drive the words are about transforming data. And holding more data means being able to make more decisions, and our platform can provide more possibilities. When the complex world needs to add a new driving force, it needs to be very scalable and flexible. In DAOD ECS mode, a world is a collection of entities. Each entity uses the data to describe. Each system is a driving force. Using data-oriented design has many advantages. In addition to the strong scalability mentioned before, network synchronization will be much easier. Organized data makes the maintenance, debugging, and concurrency much better. If the system task is heavy, the system's tick rate can be reduced. We can control the performance in some way, and trunk data can be processed easier. Machines can be effectively handle the data in DoD principles. Next, we talk about network synchronization. Some component data are marked as synchronization, such as position information. When data changes in this frame, the data will be synchronized to the remote. The benefit is that there is no need to call RPC frequently, and the registering callback function for the client or servers can make the code complex. In addition, synchronization based on the component data can also hold the data, making it easier to be driven by the logic-driven force. For example, driven by the simulation system for prediction. And let's compare OOP and DoD. Object-oriented programming lets you mix the data and the behavior. It causes a column-wise traversal jump in the memory, resulting in cache miss and CPU stalling. But hardware doesn't like objects. Data-oriented design uses a row-wise traversal memory access pattern. Meanwhile, the data is all efficiently organized in tightly packed continuous arrays and filtered behind the scenes. The benefits are immense. It improves the access line with the cache efficiently and can save the memory as well. The CPU uses the virtual address to access the cache memory. When the CPU addresses the memory, it first sends the virtual address to the cache memory. If the required data is found in the cache memory, the CPU will not access the TLB and DDR, which will improve the processing speed. Data arranged neatly in the CPU can be quickly combined into snapshot trunk data during the game process. Snapshot trunk data is periodically recorded into a dynamic buffer elements. Snapshot trunk data can be used for many purposes, and it is a key information to describe the experience of the world. When playing the game with friends, the data of each entity constitutes the world's runtime data. When editing the game and organizing the configuration, the storage of each project constitutes UGC data. Every asset used in the world, every object that is presented in the world constitutes asset data. Runtime data, UGC data, asset data constitutes the world, and many worlds together makes the metaverse. And the metaverse is the data. This is the Yahaha pipeline, which provides a comprehensive solution for users to create a world. Share the world and experience the world. It's time to start creating the metaverse. You can freely create and edit the project, and wherever you are, your project data will follow you. You don't need to worry about how to synchronize your project anymore. You can quickly select assets for prototyping without worrying about how to download the assets. You can upload your own created assets without worrying about standardization and optimization assets. You can choose the gameplay components to quickly make your game alive without worrying about coding skills. You can quickly create logical connections without having to remember the clear syntax of the APIs. If you are an ordinary creator, you can choose a template to start with. If you think creating world is too complicated, AIGC can arrange the scene and logic according to your wishes. In Yahaha, you can highly customize the words if you want. Anyone can Yahaha, and we are aiming to improve the Yahaha and make it better each day. Yeah, that's all. Thank you for your attention.